So here's number 33 from the worksheet. Um, and for this problem, we have to do a few things. We have to plot the graph. They say using trace, and I'll show you that on there to find the approximate x and y coordinates of all the maximum, minima, and points of inflection. And then find the global maximum and global minimum. Then find the first and second derivative to algebraically figure these things out. And then to show how the second derivative test applies to the leftmost interior critical point, we just find the second derivative test and show that it works out, and explain how you know there are no other critical points or points of inflection. Okay, so there's all these parts to it. So first of all, we've got to look at the graph for number 33. So y equals, for this function, negative x cubed plus 5x squared minus 6x plus 7. So let's graph it, see if we can see everything in the window. I get a decent view for this one. I'm going to just change the window to make it a little higher on the graph though. Make the y max like 15 or something, just to give us a little better perspective. And then I also notice it doesn't have a lot in the left screen, so I don't know, it's negative 5. See if that just gives us a little more, a better global view of what's going on. Okay, so that's a little better. So trace. So start from the left. So it's concave up here at this point. The minimum looks like it's around x equals, I don't know, 1 or so, or maybe 3/4 or something like that. We'll just see when we get there. It looks like there's maybe a point of inflection here at x. Oh, I'm sorry, in the minimum value, which is a relative min, is about 5. So it's around 1 and 5 somewhere in there. We'll see what that actually is when we get closer to it. Point of inflection is somewhere at like, I don't know, 1.5, comma 6 or something like that. And now it's switching from concave up to concave down. Our relative max is looks like about 2.5, comma 7 and 5/8 is what that is. So about there, and then moves there. Those are relative max and mins because the graph goes up forever to the left, down forever to the right, so it doesn't do us any good there. So let's start jumping into actually doing stuff to analyze this. So let's see. I've got the function number 33. F of x equals negative x cubed plus 5x squared minus 6x plus 7. So going from there, the first derivative is negative 3x squared plus 10x minus 6. And then our second derivative is negative 6x plus 10. Okay. So the second derivative will be easy to solve for. The first one looks like it's going to cause us a little bit of pain to do. We may need to do then the quadratic formula for that. So let me show you a little trick here on the graphing calculator. I mean, we know the quadratic formula. Let's see if we can find these zeros without them actually having to be exact. So what we can do is we can actually throw into the graph, into the y2 window, y2 function, the first derivative. And how you do that is you do math, scroll down to end derivative, and then you say, okay, what variable do I want to differentiate with respect to? Well, with respect to x. What's the function? Well, I could type all this in here, but I'm going to cheat even more. I'm going to say, let's put y1 in for this. So y1. And then it's going to ask you what I want to differentiate it at. Now, if we're doing this in the home screen, I want to find the derivative at a point. I put a number in. But since I'm going to graph this, I'm going to plug x in. And now what it'll do is it'll graph this derivative in for the graph. Now, one thing you want to make sure that you also do is you also scroll up to here over the equal sign for y1 and press enter to make sure that it's not highlighted like it is right here, because I want to turn off the graph for y1. And then push graph. And it's got to think. It's going to take some time. But what we can do then is I can find the zeros of this graph, and that'll give me at least approximations. And maybe what I'll find out is, okay, they're not nice numbers. I'm going to have to do the quadratic formula if I want exact values, but I can at least find some approximate values. So to do that, you push second, calc, and I want to find a 0. So that's where it's going to be this guy here equal to 0, because that's what I've got graphed in there. So left bound means just go left of the 0. So I'm going to do that first here on left. So this is left of it. Press enter. Right boundary means just go to the right of it. Press enter. And then guess. You can just press enter again, but if you want to scroll closer to it to make it a little nicer, you can. And here's what I was afraid of. We get 0.78474975. Probably not a nice even value. Okay. So what we're going to have to do is the quadratic formula for this. So 0 equals negative 3x squared plus 10x minus 6. Now one of the things I always teach in Algebra 1 when we do the quadratic formula is to make all those opposite signs to keep a positive. So 0 equals 3x squared minus 10x plus 6. And now we just jump into our quadratic formula. X equals the opposite of b, 10, plus or minus the square root of b squared minus 4ac. Well, that's going to be 100 minus 4 times 18. And just to make this easier, b squared, which is 100, minus 4 times 3 times 6. Which is 28. So yeah, that's why we didn't get a nice number. And then all over 2a, which is 6. It does simplify, it does simplify some. It's 10 plus or minus 2 root 7 over 6, which gives us as exact values. Divide all those outside by 2. 5 over 6 plus or minus root 7 over 6. Sorry, no, over 3, because we divided the 2 out. So there are exact answers. Okay. Now, for us to do that derivative test, we just need to know what they are approximately. So again, you can plug it into the calculator and do the approximate, or we already knew the left one was at 0.7. Oh, what was that? Let's go back to the graph. So second calc 0. Left bound was let's go left of it. Right bound. Guess. So 0.785, let's say, approximately. The other one, we'll do 0 again. Second calc 0. Again, left bound. I want to go left of that 0, which actually is above it because of the way the graph is shaped. Then to the right of it. And then guess 2.54849. Again, I'm just approximating. And now I can test numbers in this guy here to left and right of it. Now, another way you could do this as well, if you wanted to do it without plugging all the way in, is you could do the derivative of the first function and evaluate at numbers left of this. So you could do, and here's a quicker way to do that even. Do in deriv, math 8, respect to x, and then variables y1, and then the number. Well, what's a number left of 0.785? Would be 0. That's a number left. Okay, so negative, there's our 0 slope. And then you can do second enter, and it pulls it back up again. And now scroll down to here and change your number. What's between 1.785 and 2.5? I don't like 1.5. 1.5 has a value of 2.25, which is what it is. So positive slope. Here's 0. And then try it to the right of 2.549. So like 3.5, which is negative again. So negative 7.75. Again, this is a lot of times like a round off error over here. So it's negative, which we could see that in the graph as well. Negative values, because remember this is the derivative, so we're not looking at the slopes, we're actually looking at the values. So negative, positive values, negative. Negative, positive values, negative. So I know that this is a minimum, this is a maximum. And they're both relatives if I look back at the original graph. So relative, min, relative max. Okay, now the next part of this is to analyze the second derivative. So this one I can actually solve easily. Just set it equal to 0. We get then x equals 5/3. So that's the x value of the second derivative. So 5/3 is really 1 2/3. If I plug a number in left of 1 2/3, I get for this positive, because I get 0 here. You can just, if you need to test that real quick just to make sure, like maybe 0 in there. -6. Negative 6 times 0, which is 0. Oh, I'm sorry, plus 10. Don't forget to add the plus 10 there. So that's not right. So plus 10, which is positive. And then throw a number to the right, like, I don't know, like 2 in. So -6 times 2 plus 10. -2. Slope is negative. Okay. So, or not the slope, the concavity is negative. So it's concave up, concave down. Now, the last part of this then is to actually find those minimums, find those maximums, and the other part of the directions was to verify, okay, that the second derivative test works for the leftmost critical point. Well, here's the leftmost critical point. It's 0.789. It's a minimum by the negative to 0 to positive slope, but also it's concave up there, and the second derivative test tells us if you're concave up and you're in your critical number, you have to be a minimum. So it matches that. Plus the rightmost one is where it's a maximum and it's concave down. So again, in order for you to be a minimum, like here, the graph has to be concave up. In order for you to be a maximum, like here, the graph has to be concave down. So it is for those two portions. Now the last bit of this then is really, and how do you know there are no more critical points or points of inflection? Well, it's a quadratic. We found 2 solutions. So 1 solution, 2 solutions, we know there are no more there. And then for inflection points, it's a linear function. There's only 1 solution. We found that. So that's the way we get around that. Now our last bit then is to really actually kind of go back to B. And it says find the precise x coordinates. Well, we've already done that. Here are the x coordinates for the min and the max. So minimum at x equals 5/3 minus √7/3. Max at x equals 5/3 minus √7 or plus √7/3. And then it said the x coordinates. So we only need to find the x's. And then the inflection point is x equals 1 2/3. Sorry for the sloppiness. This was 1 2/3. There we go.